Hello everyone, this is part 2 of the review tutorial for ENGG 2430A. In this part, we will review the topics we learned at week 3 and week 4, including the measures for calculating probability and the concept of independence. Let's first review the measures for calculating probability by an example here. The class consisting of 4 postgraduate and 12 undergraduate students is randomly divided into 4 groups of 4. What is the probability that each group includes a postgraduate student? An intuitive method for calculating this probability is by counting. We denote the 4 postgraduate students by 1, 2, 3, and 4. Then the problem is how to put the 4 postgraduate students into the 16 positions such that each one is in a different group. Obviously, the sample space S is all the possible positions of the 4 postgraduate students, and our desired outcome A is the assignment of positions when the 4 postgraduate students are in different groups. So the size of S is equal to 4 factorial times 16 choose 4, while 16 choose 4 means we randomly choose 4 positions for the 4 postgraduate students. 4 factorial means the permutations of the 4 students on the 4 chosen positions. Pay attention to the term 4 factorial here. Since we have 4 different postgraduate students, their orders of positions matter for the final result. In other cases, when orders do not matter, combinations should be used instead of permutations here. For the size of A, it is equal to 16 times 12 times 8 times 4, which means for student 1, we have 16 choices. Once the position of student 1 is determined, we only have 12 choices for student 2. Similarly, we have 8 choices for student 3 and 4 choices for student 4. So, after some calculation, we find that the probability of A is equal to 64 over 455. We now introduce another method by conditional probability. We still denote the 4 postgraduate students by 1, 2, 3, and 4. And the problem is how to put the 4 postgraduate students into the 16 student slots such that each one is in a different group. Consider the following events. A1 is student 1 and student 2 are in different groups. A2 is student 1, 2, and 3 are in different groups. A3 is student 1, 2, 3, and 4 are in different groups. So the probability of A3 is equal to the probability of A1 and A2 and A3. We expand this term based on multiplication rule and obtain that the probability of A3 is equal to the probability of A1 times the probability of A2 given A1 times the probability of A3 given A1 and A2. For the probability of A1, it is equal to 12 over 15, since there are 12 student slots in groups other than the one of student 1, and there are 15 student slots overall, excluding student 1. Similarly, the probability of A2 given A1 is equal to 8 over 14, since there are 8 student slots in groups other than the one of students 1 and 2, and there are 14 student slots, excluding students 1 and 2. Also, the probability of A3 given A1 and A2 is equal to 4 over 13. Since there are 4 student slots in groups other than one of student 1, 2, and 3, and there are 13 student slots excluding students 1, 2, and 3. So the desired probability is 12 over 15 times 8 over 14 times 4 over 13, which is equal to 64 over 455. Actually, we can use a tree diagram to show such a process. And the final result is to multiply all the probabilities along the desired branch of the tree. From this example, we can see that, besides direct counting, we can also use conditional probability to break a problem into multiple easy sub-problems. And diagrams such as Venn diagram and tree diagram help us a lot for showing the process. There also exist other tricks for calculating probability, which is left for you to find during your self-practice. Now let's see another example on the second topic, independence. We have learned how to prove the independence of events in the previous lectures and tutorials. But how could we apply the independence concept when solving problems? This example will show that to you. A pair of fair dice are rolled until a sum of 5 or 7 appears. Find the probability that a 5 appears first. For one round of experiment, the sample space is given by the possible outcomes of the 2 dice. If we want to get a sum of 5, there are 4 possible outcomes: 1, 4, 2, 3, 3, 2, and 4, 1. Similarly, if we want to get a sum of 7, there are 6 possible outcomes: 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So the probability that we get 5 in one round is 1 over 9. The probability of 7 is 1 over 6, and the probability that we get neither of 5 or 7 is 13 over 18. Now consider rolling the dice until at round end a sum of 5 appears. We represent such an event by En, which means we get neither of 5 or 7 in the first n-1 rounds and get 5 in the nth round. So the probability of En is the probability that we get neither of 5 or 7 in the first round and in the second round until in the n-1 round and get 5 in the nth round. Since the result of one round is independent of the result of another round, we have the probability of En is equal to the multiplication of the result of each round. For every round, the probability of different results are listed above. So we have the probability of En is equal to the probability that we get neither of 5 or 7 in one round to the power of n-1 times the probability that we get 5 at round n. The final result Pe is hence given by the summation of P of En for all n. Based on the formula of geometric series, we get the probability that a 5 appears first is equal to 2 over 5. For this problem, the understanding of the independence of each round is important. Based on this, we can represent the final probability by the result in one round. This is the end of part 2 for the review tutorial. Thank you for watching.